So my topic today is my old favorite, the meaning of probability. I actually a couple years ago was talking to a friend of mine, and I said, I love this material so much. You could literally wake me up in the middle of the night and ask me to give a 45-minute talk on the meaning of probability, and I'd be happy to do so. And here we are. Um, so I guess I should be more careful when I say such things because the universe will find a way to test me. But here we go. I want to talk about these ideas themselves, and I think in many cases these are probably things that you're familiar with. Maybe a little bit of a new take on one or two things, but I think I also want to simultaneously talk about teaching probability this way. And I think last year when I spoke at this group, I said something to the effect of, if you're not teaching probability, or if you're teaching probability and you're not mentioning Cox's theorem, then you're doing something wrong. And in case you didn't take that advice, or that's something that you haven't yet been able to do, I think I want to maybe share some kind of practical vision of what that could look like. In particular, this is drawn from my own teaching experience at the Harvard Extension School, where I teach a very introductory level course to students who don't have a very advanced math background, but people who have been struggling with probability and statistics kind of in their own work. And I found that this does help to kind of make some things make sense in ways that the traditional approaches to probability don't really satisfy. So just by way of motivation, we'll start with the classic question of what is probability, or maybe what the belief is probability. And there was an interesting kind of thing that happened on Twitter about 2 years ago. Richard McElraith, who I'm sure many of you know, he's the author of Statistical Rethinking, and he's also a professor of anthropology, someone who works in the field with real anthropology data. Said something in response to a question about the meaning of probability. He said that in my anthro and bio work, the debates and confusion are about new things. Okay, but in my stats work, the debates are about what the F probability means. And stats is like an inverted field in which everyone uses linear regression, but no one agrees what it means. And I thought that was really a perfect kind of encapsulation of the foundational issues that we have in statistics, where many people kind of arrive at similar looking or quantitatively similar looking tools, but there really is a kind of fundamental confusion about the very nature of probability, or what we're trying to accomplish with these tools. And then just a couple of weeks later, a few days later, as if to prove his point, there was this exchange between a couple of statisticians. Carl Rowe, who's at University of Wisconsin, said, "I no longer know what 30% chance of snow means. Honestly, no clue. Being an academic has wrecked my brain. Am I crazy, or are they crazy? Send help." And Daniela Witten, who is professor of statistics and biostatistics at the University of Washington, and again, very prominent statistical writer and thinker, said, "Ugh, so much of this, like, what does this mean that over 100 realizations of the universe, it snows in 30 of them, please send help." And I think it was just interesting to underscore the fact that these people who are very sophisticated in this field, and really kind of thought leaders in statistical techniques, when it comes down to the basic questions of kind of what does probability mean, how do we make sense of a probability statement like the percent chance of snow, that there is a kind of fundamental confusion, and also I think a little glimpse of kind of leaning back on an idea of probability as relative proportion, okay, or maybe frequency. And that is oftentimes where people tend to go. So I think as Bayesians, we have this particular challenge of trying to model a new way of thinking about statistics and new techniques. And if we get into really the minutia of a debate about some of the philosophical issues about, I don't know, optional stopping or other things. At the end of the day, I think you will oftentimes find yourself having this conversation of what is probability anyway, and nobody really knows. Is the bottom line. So that's what I'm going to try to help with today, hopefully. There's obviously a lot more than one presentation's worth on that material. So I just put, I think, here a few of my kind of go-to summary references. Everyone, I think, has their own, but the ones that I find myself often turning to get kind of a survey of the thinking along various lines are some of the books mentioned here, particularly 10 Great Ideas About Chance, the Diaconis and Skirms book from a few years ago, I think is an excellent kind of reference if you haven't checked that out. And Jaynes, my muse, I always return to when I need some orientation. The particular kind of presentation of the Cox's theorem version of probability that I'll be talking about today is worked out in greater detail in this paper from a few years ago that I wrote with Travis Waddington called Bridging the Intuition Gap in Cox's Theorem, a Jaynesian Argument for Universality. So that's where you'll find some of the kind of technical details if you're interested in. And I'd love your feedback on that. I haven't gotten a chance to really present this much in the last few years. So that's great. Okay. So again, I think to kind of set up the problem, I'll start with something that you probably all know, or at least I think we can agree on that no conventional definition of probability is adequate to handle all the ways that probability is used in practice. Okay, so if we think about the ways that probability is usually presented in, textbooks or at the kind of intro level, there's usually just kind of a couple ways that's defined or presented. And typically the main kind of school of thought is it has something to do with relative proportion, okay, of possible outcomes, sample space, blah, 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 or frequencies of occurrence over the long run. But if you want to define things that way, then you have to deal with or somehow explain how do you use probability when you're talking about one-time events or events in the past, okay, things where there is just not an obvious kind of relative proportion or frequency interpretation. So for example, if we want to ask what meaning do we ascribe to the statement? How can we make sense of a statement like that Trump had a 29% chance of winning the 2016 US presidential election? We really can't make sense of that. Well, in a number of ways, we can't make sense of that, but we can't make sense of that in terms of a relative proportion. What are the 100 possible universes of which 29% of them had that event occurring? Or, in what sense is that the true frequency over some long run of trials of that election? But kind of simultaneously, or in contrast to that, if you want to define, I think as we do, want to define probability as a degree of belief, then how do we make sense of events with a known frequency, or things where we have a kind of right probability we're supposed to arrive at? So for example, if we're asking what are the fair odds for a bet in a gambling game like say roulette, we know there's a right answer, but the degree of belief interpretation doesn't seem to specify that for us, right? So we have to somehow make sure that we get the numbers right for instances like this. And so I think there's this natural kind of tension. When you really boil it down, I think these are the sort of two main schools of thought about what probability means, and neither one of them really seems to satisfy all of these possible situations. So just a little bit kind of as an aside, which I think is maybe a way that some people attempt to address this, is to think about probability in terms of betting prices for gambling games or contingent bets on various outcomes. So this goes back to the work of Frank Ramsey and Bruno Definetti, 20s and 30s, who defined probability in terms of the prices paid for bets on various outcomes. And what they showed is that if you are sort of coherent in your betting price and there's certain assumptions are satisfied, that those betting prices must satisfy the rules of probability. Okay, so probability kind of arises naturally from the arithmetic of these betting prices if you assume that there's no possibility of a risk-free loss or gain. And if you look that up on, say, the Stanford Encyclopedia of Philosophy, you'd see material like this where it goes through the argument of, if they don't satisfy the rules of probability, then you can kind of construct bets with risk-free profits or losses. And this can also apply to kind of conditional bets and so on and so forth. The problem is, first of all, that is sort of manifestly not how people and markets actually behave with respect to probability and price. That if you go ask, a bond trader, what is the probability of a bond defaulting, and then you ask them, okay, now what price do you associate to that for that bond? You get different answers because there are such things as risk premia in the market. Okay, prices don't exactly track the probabilities. Investors require kind of compensation for taking on risk, et cetera, et cetera. So there's already this kind of disconnect. And I think economists have ways that they try to get around this with utility theory and, risk-adjusted probability or risk-adjusted price, et cetera, et cetera. Don't need to worry about that too much because really the bigger issue is coming back to the previous slide. It doesn't tell you what the answer should be. Right? All this kind of school of thought can ever do for you is tell you how probabilities should be related to each other, right? If the prices are coherent, then they have to satisfy these certain rules, but it doesn't tell you what the price for a particular event should be. Okay, so we come back to the question of, well, how do we know we get the right answer when there is a probability that's supposed to match some kind of empirical frequency or some, supposed to be a kind of right answer to the question. So we can kind of just sidestep that whole approach. I think the other thing, kind of unfortunately, that a lot of people tend to lean on is the measure theoretic axioms of probability. Right? So they would say, well, no, we'll just define probability as this, measure space, and we have words like sigma field and countably additive set function and sample space and so on and so forth. That also doesn't really help. And the reason it doesn't help is, I think, an issue that we don't really give adequate attention to, which is, why are those the right rules? In other words, why are the rules of probability the rules that they are? And when we talk about the rules, what we really mean by that are two basic properties of probability from which all the other ones kind of follow. Okay, and they are the probability of the negation of a statement or an event is 1 minus the probability of that event, and that the probability of the combination A and B is related to probability of A and probability of B given A in this way. And if you think about relative proportions or frequency interpretations of probability, these things just come for free because these are properties that proportions satisfy. Okay. But if we are trying to kind of start over and define probability in terms of degrees of belief, it's not at all obvious why the degree of belief of something should satisfy this equation. Okay, or the degrees of belief of two things should satisfy this equation. So those axioms that we had in mind, you would just have to kind of take them on faith or take them as given if you wanted to think about probability as something other than relative proportion. And this actually has come up in the kind of very long history of argument about the nature of probability, going back to even in the 30s, when there was this very kind of public exchange between Ronald Fisher and Harold Jeffreys, arch Bayesian. Harold Jeffreys, they had this public kind of debate in the proceedings of the Royal Society. And one of the points that Fisher picked up on was this, that Jeffreys had defined probability as the kind of degree of logical support of one set of information supporting another set of information, and said that you could combine probabilities with these rules called addition and multiplication. And Fisher kind of pounced on that and said, this is going back to an idea of Keynes's in 1921, the logical theory of probability. He said Keynes establishes the law of addition and multiplication of probabilities, but the important step of showing that when these probabilities have numerical values, addition and multiplication, as so defined, are equivalent to the arithmetical processes ordinarily known by those names, is omitted. The omission is an interesting one since it shows the difficulty of establishing the laws of mathematical probability without basing the notion of probability on the concept of frequency, for which these laws are really true and from which they were originally derived. And it's probably maybe the only thing that Fisher's ever written that I agree with. But I think it happens to be a very good point that that's where the rules originally come from. And if you go back to the writing of Kolmogorov, for example, who's responsible for that axiomatic approach that I showed on the previous slide, he even said kind of later, I think, on that axiomatic system only applies to the real world. The basis for the applicability of the results of the mathematical theory of probability to real random phenomena must depend on some form of the frequency concept of probability. Okay, otherwise, why would those be the right rules? And if you look at even contemporary textbooks like Pittman's book, my colleague Jim Pittman at the University of California defines probability at the very beginning of the book as an extension of the idea of a proportion or a ratio of a part to a whole. And I think this is the reason why the first examples of probability in any intro textbook are always counting up the ways that, say, 2 dice can add up to a certain number, or 2 coin flips can have a certain number of even and odd, because you have a very obvious kind of sample space of possible outcomes, and you're defining probability as the relative proportion. Okay, so if we want to kind of shake people of that conviction and move them off of that interpretation of probability, we have to, I think, have a very compelling answer to the question of where do these rules come from? Okay, and this is what Cox's theorem does. Okay, so this is why I think, as I said about a year ago, if you're teaching probability and you're not mentioning Cox's theorem, you're missing something kind of fundamental, because the only way that I think that you can motivate the rules of probability in any other way besides defining probability as relative proportion is via something like Cox's theorem. Or at least it has a strategy that could be very successful. And I think in doing so, it allows you to kind of scrap that whole program of defining probability that way. And then you don't run into this problem of, okay, now how do you define probability in a way that satisfies all these possible applications? Because you have one unifying definition, which we'll get to. And that, as the title alludes to, can be the one probability that applies to all situations, the one probability to rule them all. So what does that look like? Well, for one thing, we have to start over and forget about the concept of probability for just a bit and define as this symbol, which we'll say is parentheses wrapped around A conditional on X, to just represent something called plausibility of that statement given that background information. Okay, so that's really what we're talking about in this Cox's theorem approach, is a numerical representation of plausibility, whatever that means. And instead of kind of axiomatizing that in a way that satisfies the rules of probability, all we're going to do is say, let's assume that these plausibilities satisfy certain kind of common sense rules. And we'll get to the rules in a couple of slides, but the idea of the rules is that they are just showing you the kind of the direction that these things move, right? So saying how they go up and down, and that they have a kind of logical respect for, they are logically consistent in the sense of respecting the propositional calculus. Okay, and we'll get to that in just a minute, what that means. And assuming that's all in place, what this kind of wonderful theorem tells us, going back to Cox in the 40s, is that you can always then rescale a system like that of plausibilities so that they satisfy the numerical rules of probability. Okay, so basically what that tells you, or that gives you, is a way of interpreting probability as just this numerical idea of logical plausibility that's been put on a convenient scale. Okay, so it's like a system of units that you can express plausibilities on that kind of make the equations look nice. Okay, and the equations happen to be the equations of probability that we're all familiar with. So that is really the kind of essence of Cox's theorem and what this presentation of probability gives for you. And I think then you can kind of see the power of that if you can derive the rules of probability from just these kind of more basic or more fundamental common sense rules of plausible reasoning, then that can apply to every situation. You don't have to be tethered to kind of the idea of probability as relative proportion. You can say, okay, no, in any situation where we have some information, we have a proposition kind of partially entailed by that information, we can talk about how plausible it is. Okay, and then probability is just basically that in numbers on a convenient scale. Okay. I just want to check. I'm not able to see or hear any audience feedback, so I'm hoping that we're all okay. But I don't know if we're not okay, then maybe somebody can give me a thumbs down or something. Yeah.
It's all fine. We're all here, and we hear you very well, Aubrey.
Great. So. Okay. And we're following along. Okay. Fantastic. Okay. So now we get to the real kind of the meat of the subject. And I should maybe give a little bit of warning that this does get a little bit mathy at times, but I think again this is meant to be suitable for a kind of intro level probability and statistics curriculum. So hopefully you'll agree with me. So if you are going to start thinking about probabilities this way, or teach it, the first thing you need to do is kind of just do a little bit of review of logic. And when I mentioned the propositional calculus, okay, propositional calculus means, as it says, kind of arithmetic on logical propositions. Okay, so propositions are just statements, and they're particular statements that can carry truth values. They can either be sort of true or false statements. And the important thing about propositions is that they can be combined. There's an arithmetic on propositions using these things called logical connectives. Okay, so we usually represent propositions by capital letters. Okay, so let's say we have two propositions, A and B, and we can build up this table that represents all of the possible truth values of A and B, and then talk about these other propositions that are usually denoted as shown here. So this is the proposition not A, which just has the kind of opposite truth values of whatever A has. Okay. The proposition A or B, which is written A plus B, kind of, I hope for obvious reasons, that it is the proposition that is true if one of A or B is true and false otherwise. Proposition A and B is the one that's true only when A and B are both true. And then other ones like the implies proposition, okay, A implies B, material conditional proposition is kind of has this truth table. The funny case is the one I've shown here. We have false implies true is actually true, okay, for reasons that we won't get into. But that's the important thing, that basically you think about propositions as carrying these truth values, excuse me. And then you can start building up ones from those ingredients. And the only thing you have to really keep track of is what truth value does the new proposition have in any one of these cases. And the other important idea then that we need from this propositional calculus is the idea of logical equivalence. Okay, so we'll say two propositions are logically equivalent and write them with this triple equal sign. A is logically equivalent to B if they always have the same truth value. So the kinds of things that we're talking about are, you know, the commutative and associative rules of these various logical connectives. So like P or Q is logically equivalent to Q or P. Okay, pretty obvious from that truth table. P and Q is equivalent to Q and P, et cetera, et cetera. And then maybe even more complicated ones like the not of the and of P and Q. Not P and Q is not P or not Q, one of De Morgan's laws, and so on and so forth. And you can play around with these and build up all kinds of possible different logical equivalencies. But the point is, we now want to put all of that into a framework of reasoning about plausibilities of these propositions, given given background information or given other propositions, essentially. Okay, so when we talk about these common sense rules that we'll have in the Cox's theorem version of plausible reasoning, they look like this. So the first idea is that the plausibility is just a real number. Okay, when we talk about plausibility of A given X, it ranges from 0, which represents impossibility, to 1 representing certainty. Okay, that's fairly arbitrary. You can easily rescale that from any other interval you want, but that's going to be our convention. The second common sense rule is that the plausibility of the negation, not A given X, is completely determined by the plausibility of A given X. Okay, so there just is some rule, it can be any rule you choose, that means once you know the plausibility of A, you also then know the plausibility of not A. Okay, it doesn't have to be one of the rigid rules of probability, but it's just something that tells you that one is determined by the other one. Okay, and they have this relationship that if A is made more plausible, given X, for whatever reason, maybe you have new background information and A becomes more plausible, then not A should become less plausible. Okay, so fairly intuitive, I think, about what we would expect from a numerical representation of plausibility, that negation and plausibility of the statement are kind of related to each other this way. Okay, second one, a little bit then similar, but slightly more complex looking, that if you have these two ingredients, plausibility of A and plausibility of B given A, that should somehow be everything you need to construct the plausibility of A and B. Okay, so Jaynes goes through a little bit more of a discussion here. I think this is fairly intuitive if you think about, what would you need to reason about the plausibility of a combined statement A and B? Well, you need, one of the ingredients on its own. Okay, it could be A or B, and then you need something about the interaction between the two. Right? So you need to think about, if you have one thing, what does that tell you about the other one? If you know those two plausibilities, then it's, I think, reasonable to assume or to postulate that you have everything you need to build up the plausibility of A and B. And they should behave directionally kind of as an increasing function of both of those. So if either one of them, the two constituent parts, kind of becomes more plausible, then the combinations should become more plausible as well. Okay, so that's kind of category 2, rule 2. And then rule 3 is the one about the propositional calculus. Okay, so there's two kind of important sides to this. So one is shown here, and this looks a little funny when you first read it, but it's actually very intuitive, that if you have background information X and A, proposition you're reasoning about, and another set of background information X prime and proposition A prime, if it's the case that X and A is logically equivalent to X prime and A prime, okay, then the plausibility should be the same. And now one way that this can immediately be satisfied is if A and A prime are the same. So this is saying, in special case, if the background information is kind of written in a logically equivalent way, you should always get the same plausibilities for any proposition. Okay, that I think is very natural and intuitive. But the other way that this comes up is that what this is saying is that if A and A prime are kind of logically equivalent within the logical context of the background information. Okay, so you kind of don't care ultimately what happens when the background information is not true, because you're sort of conditioning on it. So if it is the case that when you and together with the background information, X and A is equivalent to X prime and A prime, or X prime and A, or whatever, that's the case you care about. And in that case, you should have the conditional plausibility being the same. Okay, that is what we mean by kind of respecting the propositional calculus, or respecting logical equivalency. And then the last thing just basically has to do with the labeling of propositions. Okay, so we build all this up from kind of assigning capital letters to propositions. And the last kind of assumption is that, well, okay, if we change our labels, relabel every proposition in the problem by some other labeling scheme, and apply that simultaneously to the proposition we care about and our background information, then we should get the same plausibility. Okay, so there's nothing special about that labeling. If we do a translation into a different labeling system, the numbers are going to be the same. Okay. Now that seems very kind of, I think, unassuming, but this turns out to be the really powerful assumption we'll get to in just a slide. But that's it. So as far as, the rules of plausible reasoning, this is all we need to assume. And I think every one of these, there is kind of a very natural kind of intuitive support for. And the important example then that you can actually compute is something like the following. So let's say that you have now a situation of a very simple amount of background information. So suppose that an urn contains a red ball and a blue ball, and we're going to pull exactly one ball out of the urn. How do we represent that logically in this schema? Well, the first way you can think about it is, let's label the proposition A, you draw the red ball, and the proposition B is you draw the blue ball. Okay. And then our background information, what the problem has told us, can be kind of encoded in this one statement that we have A or B is true, but it is not true that A and B, right? So we draw one ball or the other ball, but not both of them. And so we can encode that with this logical connective statement, A or B, and not A and B. Okay. However, we are also free to label the propositions differently. Right, so we imagine kind of a change of labels and say, okay, let's reverse the labels A and B. So B is going to be you draw the red ball, and A is going to be you draw the blue ball. Right? What does our background information look like? Well, if we do that translation, then we have kind of similar to the previous one. We have B or A, and not B and A. Okay, and all we've done here is just kind of every place we saw an A, change it to a B, and vice versa. And we've encoded the problem in a completely equivalent way just by changing the labels. But the important thing that you realize when you do that is that X and X prime are logically equivalent to each other. Right? This statement for any two propositions A and B is logically equivalent to this statement for any two propositions, for the same propositions. They have the same truth values. And so what that means is that if we go back to thinking about the plausibility of A, okay, by our assumption 3, that has to be the same as the plausibility of the translation of A, given the translation of the background, which is just B, given this X prime background information. But now X prime is logically equivalent to X, so by our rule 3 first part, we know that that's got to be the same as B given X. And so altogether, the plausibility of A given X has to be equal to the plausibility of B given X. Okay, and so these two propositions have to have the same numerical value. And that's the key thing, that because of the symmetry of this background information, according to these rules of plausible reasoning, we must assign them the same number. Okay, we don't know what the number is, but we know it's the same value. Okay, and that is just a baby version of the kind of group invariance principle that I'll mention later on. But that's the essential idea, right? Now, situations like that you can obviously generalize. Okay, so this is the mathiest slide in the deck. So warning. But if you want to make that a more general kind of example with, say, n choices instead of 2, you can build that up just the same way. So you can say, okay, let's say we have n possible options, excuse me, A1 through AN, where we know that we have one of them, but not any two of them. Okay, exactly one of them is true. Okay, so that would look like this, A1 or AN, and not the product of AI and AJ over I not equal to J. It turns out, somewhat surprisingly, I think, that for any one of these kind of n-earn situations, if we consider the plausibility of a statement like A1 or ... or AM, the plausibility of that M proposition statement depends only on the ratio M over N. Okay, so if you had any other kind of earn or any other situation where you have n possible kind of mutually exclusive and exhaustive propositions, and they are kind of symmetric with respect to each other, or the background information is symmetric, you would always have this assignment that depends only on the ratio. m over n. Okay, so then the idea of Cox's theorem, actually kind of very shortcut to the proof of Cox's theorem, is to consider any other proposition, let's say A prime, and then argue your way into constructing an urn with approximately the same plausibility. Okay, so I won't get into the technical detail here, but basically with some kind of continuity assumption, etc., you can say that there is some n urn for some n and some m where you have a proposition like this, a1 through am, that has about the same plausibility, okay, within any tolerance. And so this ratio that we have said is the only thing that this plausibility depends on. That's what we're going to define to be the rescaled plausibility. Okay. A sort of single number that this kind of has to map onto. And I think you can kind of see that these ratios act like probabilities, right? Just like in the ordinary kind of presentation of probability, right? We have now come back to, full circle back to the idea of relative proportion and say, well, if you were, for example, talking about the negation of that proposition, A1 through AM, what is the negation of that thing? Well, in this background information, where we know that exactly one of these things is true, the negation of that proposition is the rest of them, right? AM plus 1 through AN, the OR of those propositions taken together. And so because of the translation invariance of this problem, it must be that the plausibility of that thing, right, is the same as just, well, it's some n minus m of these propositions out of n. And so that has to depend on this corresponding ratio, which is n minus m over n. But that number is 1 minus the ratio for the original proposition, 1 minus m over n. Okay, so ratios behave like probabilities. And so we get the rules of probability kind of from mapping these original plausibilities onto ratios of propositions. Okay, so if you are familiar with kind of Jaynes's treatment of Cox's theorem, if you've gone through that proof in chapter 2 or whatever it is of Jaynes, you'll see that there's a lot of artifice there about the associativity equation and functional calculus and taking derivatives and solving equations, et cetera. This is really, for me, the true essence of all of that. And I think you can cut right to the end if you have this idea of an urn, an n urn, where the plausibilities depend only on the ratios, and you can say, okay, that's the ratio, that's the number we'll take. We're going to call that the probability, and it happens that ratios obey the rules of probability. So, okay, end of story. Now, this approximately equals kind of where all the action is. So, I'll leave that for you to kind of look up. But the sort of criticism around Cox's theorem all involves these ideas of continuity and density of plausibility numbers, and knowing that you can kind of get arbitrarily close. But that's the core idea. So, if you kind of think pictorially, what this would look like would be, okay, let's say you come along some proposition, given some background information, we're going to find an urn, meaning a set of propositions, a setup like this, where let's say the A prime proposition just has the same plausibility as 6 out of those 10, right? That happens to be the M and N that work, where when you build up this proposition of 10 possible choices that are mutually exclusive and invariant, that 6 out of 10 has the same number. Well, then if you think about not A prime, it would map on to the remaining 4, right? And so these numbers, 6 out of 10 and 4 out of 10, obey the sum rule probabilities. Okay, and similarly for combinations like A and B, you could have 2 urns and sort of that are independent of each other and so on. Right. So that's the basic presentation. And then once you have that, you can kind of do all kinds of fun exercises. So one that I just kind of threw down here for to kind of show off maybe the power of this or the fun of this is to imagine, all right, let's say that we know that our background information is A or B, and we're asking for the probability of A. right? Now, probability in this rescaled, sense of Cox's theorem, or the Cox's theorem gives to us. What could we do with that? Well, let's imagine the state of perfectly no information. Right, so we'll call this I0. It's just the state of complete ignorance. What does that kind of give for us? In that state of no information, we have kind of a symmetry between the proposition A and the proposition not A. Right? So you can think about interchanging the symbols to represent A and not A. What do you know about A and not A? They're just mutually exclusive. And if we're indifferent to those, right, the background information gives us no reason to distinguish between one and the other, then we actually can have complete symmetry between the four possible cases: A and B, not A and B, A and not B, and not A and not B. Right? We have no way of distinguishing between them, and according to our rescaled rules of probability, they have to sum to probability 1. So each of these must have probability 1/4 under this background state of absolutely no information. And so then the conditional probability in the usual way, according to the product rule of probabilities, is probability of A given A or B is the probability of the A or B divided by the probability of A or B. And you can kind of just add up the cases, right? The numerator is the cases where A is satisfied. So in order for A to be satisfied, it's either got to be A and not B, or A and B. Okay, two possible cases and mutually exclusive. And the numerator is the three cases where A or B is satisfied. Okay, just like we saw in the truth table, it's either A and B, not A and B, or A and not B. And when you add those up in the numerator, you get 1/4 plus 1/4, and denominator you get 3/4. So the answer is 2/3. And I think that's somewhat kind of exciting and counterintuitive that you would start with this very simple kind of probability question that seems almost kind of abstract, and you end up with this answer 2/3. Okay, probably not what you'd expect in the beginning, but it comes from just this very simple idea of you can break down all of the possible cases according to these four mutually exclusive propositions that you have a symmetric kind of ignorance of. All right, so now actually, if you've been paying close attention, and had your eyes open, you notice that really, in the end, what we are doing is computing a relative proportion. Okay, so like I said, we've kind of come full circle back to this idea of probability as a relative proportion. And if you write out the truth table, you would see all we've done in the previous problem is looked at these four possible cases, A and B, truth values, counted up the ones where the background information is true, in this case, A or B, and that's these three cases, and then counted up the ones where the A proposition is true, the one we care about, and that's these two cases. And then what we said is that probability has to obey the kind of sum rule, so we end up with the relative proportion 2/3. Okay, but the key thing that I think is really powerful about this approach is it is very explicit from the beginning that the sample space, if you like, of outcomes in the set of all possible propositional combinations that we're considering is entirely just a product of our information. Okay, so in this case, it's the information of no information, right? We said, all right, we start from nothing, and we can build up this truth table of, well, here are all these propositional combinations that are sort of possible. And since we have no information, we can't distinguish between them, right? And then you can kind of make your background information some subset of those, and the proposition of interest some subset of those, and say, okay, what's the relative proportion? But at no point have you said anything like, these are all of the possible outcomes of an experiment, let's say, or these are all the possible universes that could obtain. Okay, so I think you can avoid this whole question of, out of what universe are you computing that relative proportion? Because it's very clear that what you're computing is a proportion of propositions, right, or statements that could be true given the information you have. Okay, and that's the key idea, that probability is about information, and it's about the logical support of a proposition given some background information. And I think you really get that very strongly from this Cox's theorem presentation from the first the first word. Okay, so let me just wrap up in the last few minutes and tell you kind of where things are, I think, still need to be worked out. Sort of in summary, with this idea of logical plausibility, okay, we no longer need to think about probability as a frequency or relative proportion to justify the mathematical properties of probability or the axioms of probability, okay, the rules that we like to use. Instead, what we can do from the very beginning is describe probability in terms of the plausibility of capturing the support for proposition A given information X. Okay, so that is the key concept. We kind of scrap the idea of probability and start over from the idea of plausibility as just a numerical representation of how much our background information gives us in support of a proposition A. And we assume, instead of the rules of probability, that they obey sort of common sense rules about the directional behavior, okay, going up and down, logical equivalency, respecting the propositional calculus, and invariance with respect to relabeling. Okay, and it turns out, given that very kind of modest setup, you're able to rescale those plausibilities so that they look like probabilities. Okay, Cox's theorem tells you that you can do that. The key idea in kind of building up that rescaling, I think, is this idea of translation invariance in an urn, and this very interesting concept that plausibility should only depend on the ratio of the number of propositions to the number total. That is really where probability is coming from. And when you have symmetries in the background information, you're forced to have particular numerical values for the probability. Okay, so you can say sometimes there is a right answer. Okay, when you have background information about a gambling game or physical system or whatever it is, if that information is kind of symmetric, meaning that you know lots of things about the system, but you are symmetrically ignorant to, say, the initial conditions of what's happening, then you can say, yes, for sure, in that situation, the probabilities have to be on these particular values. And so there is a right answer. Okay, and you can say, yes, I got to the right answer because my background information was true, right, ultimately. So there's not this kind of arbitrariness about the degree of belief interpretation where probabilities can just be kind of whatever number you want. They're forced to be particular things, and you can actually kind of audit and challenge the background assumptions of that model and say, okay, given that setup, you can arrive at the right answer. Or two people with that same information must arrive at the same answer. Maybe a better way to say it. So where do I think this should go? I mean, I think this is, as I said, this is a very powerful and useful way to start thinking and talking about probability. And I've gotten great response from the students that I've shared this with who have been struggling with these, I think, fundamental questions for some time, but it's not all the way worked out by any stretch. And I think that there are definitely some areas of exploration here and things that could benefit from some improved kind of communication and thinking about. And the first is this idea of group invariance. Okay, so this is just a little bit of I think an advertisement for Jaynes that the key idea, as I mentioned in this concept of an urn, is that setups like this, one of n sort of propositions being true, are symmetric with respect to the action of the permutation group. Okay, so you have this natural kind of action of the group of permutations of the symbols. And the point is that setup is invariant with respect to logical equivalency, or up to logical equivalency with respect to that group action. But you can have other group actions, right? So this is where you might imagine things like, your propositions representing the location of something, right? The ball is here, the ball is here, the ball is here, et cetera. What if your background information is kind of symmetric with respect to a translation of those propositions, right? So instead of B0, B1, B2, it's B1, B2, B3, et cetera. What would that give you? And what Jaynes argues is that that tells you some things about the probability measures that you have to assign to that, just to those propositions, basically the prior distributions, and it has to be sort of for a location parameter. Let's say it has to be a translation invariant or a uniform distribution. Okay, so this is where I think you can really get into the exciting extensions of this, which are deriving other sorts of priors to represent other kinds of symmetries in your background knowledge. Okay, so I'll just kind of hint at that. And the other thing, just to, I think, I want to leave you with, just as a provocation, is what you end up really, I think, kind of having to be confronted with in this version of probability, which is great, is the question of what do we actually know, right? Everything depends on your background information, your X, right? So, but in order to write out the probabilities for something, you need to specify what that information is, which means in some sense, you need to know what you know, right? So for any real problem, let's say you're faced with some experimental result and you want to kind of assign probabilities to it, you'd have to kind of look within and say, well, what is my background information, right? And how do I know that that's my background information? And I think what this then kind of creates is almost an infinite regress of how do you know that 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 information. And at some point you have to kind of, I think, cut that off and say, well, I don't know, right? Or I can't know everything that I know, because then how would I know that? Right. So these kind of thorny questions of epistemology almost, I think naturally kind of come up, right? When you start talking about how do I know that what I've embedded in this probability calculation is kind of an accurate representation of my true state of knowledge, right? And if I think about, a real experimental result, like this is something I just saw online this week, a claim like using the sauna reduces the risk of Alzheimer's disease, how would I assign a probability to that? Right? I'd have to think about, well, what do I know about saunas, and what do I know about Alzheimer's disease, and what do I know about this study? And I'm not even sure I could say what it is that I know about that, right? So how do I, if I can assign a prior to that, it's somehow dependent on my choice. And maybe a better way to go about it is to say, well, I don't actually know what my prior is, but I know it's in a range, right? Or I know I can say it's sensitive in some way to various assumptions, and then I can come up with intervals probabilities instead of precise numerical values. Okay, I think this might be hopefully something that comes up in prior elicitation. And do I know things like very complicated calculations? Right? Do I know if 2 to the 2 to the 61 minus 1 is prime? In some sense, I do, because I have all the information I need to calculate it, but I don't know what the answer is. Okay, so this is where I think things start to get very slippery, but also very exciting when we really have to kind of audit our background information. Okay, that's it for me. Thank you very much.